Today I'm going to introduce you to one of the most important concepts in chemistry, ionic and covalent bonding. More specifically, we will be addressing the energetics of bond formation and breakage, and how properties of the atoms and bonds themselves relate to the bond energy. After this lecture, you should be able to predict which compounds or molecules will have greater bond energy than others, based on properties like bond length and type. First, let's start with an analogy. Imagine you are holding two magnets in place on a table, oriented like this. If you release the magnets, what will happen? The magnets will move across the table due to the attraction between the north and south poles, and they will stay together until you pull them apart again. Let's think about the energetics of this example. Initially, you have to apply energy to the system to keep the magnets apart. When you release the magnets, they move until they cannot get any closer. This is a lower energy state, since you are no longer putting in the energy to keep them apart. With this in mind, is the change in energy of this system going to be positive or negative? Since the final state has less energy than the initial state when you were holding the magnets apart, the change in energy for this system will be negative. With this in mind, what would we need to do to pull the magnets apart to return to that initial state? In order to pull the magnets apart and return to the initial state, you would need to add energy. Keep this analogy in mind as we consider a chemical example. Let's imagine we have a proton, H+, and a hydroxide anion, OH-, which react to form water. How is this similar to our magnet analogy? The positively charged proton is attracted to the negatively charged hydroxide anion, like the north pole of one magnet was attracted to the south pole of the other. However, this example is not exactly the same. How is this different from the magnet analogy? Well, is this the same type of attraction that the two magnets felt to each other? This attraction between our positively charged and our negatively charged ion. In fact, though these are both types of attraction, the attraction between two ions is electrostatic, not magnetic. Let's look at the energetics of this system. Like in the magnet analogy, the energy of the separated ions is greater than the energy after they come together to form the water molecule. The energy change is negative. With this in mind, is this reaction exothermic or endothermic? Since the change in energy is negative, this reaction is exothermic. Exo, it's releasing energy. The energy is released after the two ions come together. Now, what is the source of this energy? This energy comes from the formation of the hydrogen-oxygen bond. Although the previous example talked about oxygen-hydrogen bond formation, in fact, this is generally true for all bond formation. Energy is released when bonds are formed. Now, to break the bond, energy must be added. Remember, you had to put in energy to pull apart the magnets. So if this is true, then you have to put energy into the system to break a bond. So to break a bond, the system must absorb energy. Whenever you can't remember, do you put in energy? Do you release energy? I don't know. Think about the magnet analogy. You have to put in energy to pull the magnets apart. It's the same thing for bonds. To break the bond, you must put in energy. The amount of energy that you must put in to break the bond is dependent on the strength of the bond itself. the strength of the bond depends on the type of bonding. Ionic bonding occurs when there is an electrostatic attraction between two ions, whereas covalent bonding occurs between two atoms sharing electrons. Let's start by talking about the energy of ionic bonds. The energy of ionic bonds is called lattice energy. This is the energy required to separate 1 mole of solid into its component gaseous ions. Lattice energy is dependent on 3 things: the charges of the ions, Z plus and Z minus, the distance between the ions, or R naught, and a constant, C, which varies with the type of crystal structure. Since the charges on the ions, your Z plus and Z minus, are in the numerator, as this charge increases, lattice energy also increases. For example, aluminum phosphide, which contains aluminum 3 plus and phosphide 3 minus ions, would have a greater lattice energy than magnesium oxide, which has 2 plus and 2 minus charges, which would be greater than lithium fluoride, which only has 1 plus and 1 minus. Since R naught, or the interatomic distance, is in the denominator, as lattice energy increases, interatomic distance, or the distance between the two ions, decreases. For example, the lattice energy of magnesium fluoride would be greater than that for magnesium bromide, since fluoride is a smaller ion than bromide. Now I want you to use these ideas to predict which of these compounds has the greatest lattice energy. Now is a good time for you to pause the video and consider your answer. When you are ready, hit play. Now that you have your answer, let's go over this problem. First, we must determine which of these compounds has the greatest charge, since the charge is not only in the numerator, but it is also multiplicative, so it's going to have a greater effect than the distance between the two ions. The two compounds with the greatest charge are magnesium oxide and magnesium sulfide, since sodium chloride and sodium bromide only have +1, -1, whereas magnesium oxide and magnesium sulfide have +2 and -2. In order to determine which of these two compounds that have the same charge has the greatest lattice energy, we must determine which one has the smallest distance between the two ions. Since the oxide anion has a smaller radius than the sulfide anion, magnesium oxide will have the greatest lattice energy. Now that we have discussed the energy associated with ionic bonding, which is attraction between ions, let's address covalent bonding, where electrons are shared between two neutral atoms. Let's look at a simulation of how this process occurs. Here we have 2 oxygen atoms and a graph of the distance between atoms and the potential energy. One atom is held in place while the other atom is placed a certain distance away, as indicated by the dot on the graph. When I hit play, the unpinned atom will be free to move. Let's see what happens. Why did the free atom move towards the fixed atom? Protons in the nucleus of one atom are attracted to the electrons in the other atom. However, when the two atoms get too close, the protons in each atom repulse each other. Thus, the covalent bond is formed at the distance where the repulsive and attractive forces cancel out. You'll notice that, like our example with water and the formation of OH bonds, that the bond is formed at a lower energy. However, the energy of all covalent bonds is not created equal. Let's look at some trends. If you look at this table of different bonds and their bond energies, you'll notice that as the bond order increases, as in you're going from a single to a double to a triple bond, the average bond length decreases. As the bond length decreases, the bond energy increases. Therefore, you can see the bond energy is dependent on the bond length. Now it's time for you to reflect on something you learned today, something that confused you, and something you would like to learn more about. Be sure to give me your responses, and we will continue next time.